Here we are with Alex, who is our first year science student, and it would be interesting to hear, Alex, why you chosen to study science at Monash.
Well, I've always loved science at school, and when I was picking what I wanted to do at university, it just really stuck out to me as learning more about what the universe is and why everything happens. It's exciting.
Cool. So have you chosen your major minor from the start, or you just testing around what's interesting?
Well, I could never decide what I wanted to do, so I just picked what was interesting because there's so many choices at Monash and you don't have to decide what you want to do straight away, which really works with me because I can't make up my mind about anything.
That's good. So far, what has captured your interest?
Well, I'm studying astronomy, physics, maths, and geosciences, and I think astronomy's been great, and everything's just been really interesting. There's too many choices.
Great. So what's very interesting that I find with Alex is we had in first year astronomy labs, we had a prac where we used Planet Hunters, which is a citizen project which use real data from Kepler telescope that hunts for exoplanets, which are planets around other stars. And we had certain exercises that need to be done, mainly concentrating on detecting an exoplanet. But what Alex did is not just what's required, but he wanted to go further and actually calculate what was the size of the planet. So he's going to demonstrate to us now what he done. Okay,
well, what we'd gathered from our data, which we'd seen, is we have here the measurements of the luminosity of the star. And so around here is about it's the average luminosity that we have for the star. And here we have transits. That's where the star has had the planet travel in front of it, and so has had a resultant dip in luminosity that we've measured from Earth, or up from space, Kepler telescope. And what we've seen here is we've had about a 4% dip in brightness. So we're making the assumption that a 4% dip in brightness would mean that you have 4% of the star's area being covered. And from this, that allows us to equate the area of the star, which we know, to the radius of the planet, which we don't know so far. So we have the two equations here for the area of the planet, which we can equate to find out its radius. We want to get rid of this 0.04 because it's an ugly number. So we'll times everything by 25 and get 25 times pi times the radius of the planet squared is equal to the area of the star, which is pi times radius of the star squared. So from here, we want to work in terms of the radius and not the radius squared. So we're going to take the square root of everything. And so we'll get 5. That's a horrible 5. 5 times root of pi times the radius of the planet is equal to the root of pi times the radius of the star. From here, we can sub in values that we know. We want to rearrange this to be have the radius of the planet as the subject. So we'll go RP is equal to, we'll just chuck all this on the other side, cancel out the root of pi's, to be the radius of the star over 5. So we know that the radius of the star we have up here is 486,500 kilometers over 5. That gives us our radius of the planet 973 as 93,730 kilometers, which happens to be 15 times the radius of the Earth, which means this planet's probably a hot Jupiter, because it's very close to its planet because it is a period of a few days, and it is significantly larger than the Earth.
Well, thank you for this demonstration, Alex.